Hello, shall discuss about the Zener regulators. Here, this one, it is a Zener diode, and the voltage across that Zener is Vz, and these are the whatever the input voltage which is applied at the inputs, and here it is a load resistance through which you have to get the load voltage. Now, how that Zener regulator works? Because one of the characteristics of the Zener diode is that it maintains the stability in the output voltage. Whatever might be changes in the input, but the voltage across the load it will remain same. That is one of the characteristics of the Zener diodes. That's why this diode is most commonly used in the regulators to supply a constant voltage to the load. That is one of the basic application of the Zener diodes. That it is used in the regulators. Now, the voltage V, here I have not indicated that voltage V, but here if we determine the voltage V is equal to Vi RL upon R plus RL. First of all, for voltage V, is it, because we know the input voltage which we will be applying, and we know the load resistance at the load. From that and a resistance in series with that input voltage, first of all we have to determine the voltage V. For the voltage V greater than Vz, that is the Vz is the voltage across the Zener. Here the voltage across the Zener is specified by the manufacturers of the Zener diode, so that for voltage greater than Vz, these two voltages must be compared, and when the voltage is greater than Zener voltage, Zener diode is on and is replaced by a Zener voltage that is equal to the voltage across the Zener, because the Zener diode is on and is replaced by the voltage of the Zener, that is positive, and the negative voltages. Okay, that is the voltage across the Zeners and the load resistance RL, and from that one now onwards that the load voltage across that load, it is equal to the Zener voltage Vz. Voltage across the load, it is equal to the Zener voltage, because here the only one voltage source it is present at this point, and a load resistance RL, so that here this load voltage it is equal to the Zener voltage. That is the conditions when the Zener diode it is under the on conditions. Now here if that voltage V is equal to Vi RL upon R plus RL for the voltage V less than Vz. For the voltages V less than the Zener voltage, Zener diode is off and is replaced by a open circuit. Here this Zener diode is replaced by an open circuit for the voltage V less than Vz. Zener diode is off and is replaced by a open circuit. Here resistance R, here it is the input voltage, and it is replaced by an open circuit, so that here the V is equal to Vi RL upon R plus RL, and voltage V is equal to VL, because this one V is equal to Vi RL upon R plus RL. V is equal to Vi RL upon R plus RL, so that here the voltage V, it is equal to the load voltage, because the now the voltage across this point, it is equal to the voltage V. Voltage across this point, it is equal to the voltage V. V is equal to VL because the Zener diode is off, and the current flowing through that Zener, it is equal to IZ is equal to 0. Now, when the Zener diode is under the on condition, it is under the on condition, if a KCL is applied at this node, so that here only that current IR, it is entering through the nodes, and the currents IZ and IL, those are leaving from the nodes. Only that current IR, it is entering towards the node, and this IZ and IL, these are leaving from the nodes, so that IR is equal to IZ plus IL, and IZ is equal to IR minus IL. Now, current flowing through that load resistance is equal to VL upon the RL, and current flowing through that resistance is equal to VR upon RL, and that the VR, it is then this is the resistance which is between the input and the output, so that Vi minus VL upon R, that is the current which is flowing through the resistance R. Vi minus VL upon R, that is the, because here it is in between these two. R is the VR, it is a drop of voltage across that resistance R, so that here we shall take the, if KVL is applied from that one, we will be getting the voltage Vi minus VL upon R, and the product of this current flowing through the Zeners and the voltage of the Zener, it is equal to the power dissipated in the Zener diodes. So that here this power dissipated in the Zener diode for in a Zener regulators, it must be less than PZ maximum, because here if the power dissipated in the Zener diode, if it exceeds the maximum power dissipation as specified by the manufacturers in their data sheets, then the Zener diode, it will damages. So that here, to protect that Zener diode from the damage, here the power dissipated in the Zener diode, it must be less than the maximum power dissipation as specified by the manufacturers. Okay. Here, that is how a Zener diode, it will works. A Zener, when it is used as regulators. Now we shall know about the working of that Zener regulators by one of the numerical examples. For the Zener network as shown in the figure, determine the voltage VL, that is voltage across the load resistance, voltage VR, that is the drop of voltage across the resistance R, and the current flowing through that Zener IZ, and the power dissipated in the Zeners. Here an input voltage of 16 volts, a resistance R, it is having the resistance, it is equal to the resistance R is equal to 1 kilo ohms. Resistance R is 1 kilo ohms. Okay, resistance R, it is equal to 1 kilo ohms. Now load resistance RL is equal to 1.2 kilo ohms. Here it is a Zener diode with a voltage of the Zener voltage equal to 10 volts, and the maximum power dissipation as specified by the in the data sheets of the Zener, it is equal to 30 millivolts, because here the power dissipated in the Zener, it must be less than this is the specified values. Now first thing that you have to determine this voltage, that is voltage V is equal to RL VI upon R plus RL. RL is equal to 1.2 into 10 raised to 3 upon 1K plus 1.2K into 16 volts, because this one 1.2 kilo ohm, it is the load resistance. Now V is equal to 8.73 volts. For voltage V less than Vz, for voltage V less than Vz, diode is off and is replaced by a open circuit. For voltage V less than Vz, for voltage V less than Vz, that is Zener voltage, diode is off and is replaced by an open circuit. Because Vz is equal to 10 volts, V is equal to 8.73 volts. Vz is equal to 10 volts and V is equal to 8.73 volts. So that since it is less, diode is replaced by a open circuit. Here V is equal to VL is equal to the 8.73 volts. Because already I told you that when the diode is off, the voltage across that the open circuit terminals, it is equal to the voltage V. So that V is equal to VL is equal to 8.73 volts, VR is equal to VI minus VL is equal to VR is equal to 16 minus 8.73 is equal to 7.27 volts. Since that Zener is open circuited, current flowing through that it is equal to 0, Iz is equal to 0, and the power dissipated in that Zener diode, it is equal to 0 volts, because it is totally open circuit. So that due to which the power dissipated in the Zener, it is also equal to 0 watts. Now the second condition is that here the repeat the part first with the load resistance is equal to 3 kilo ohms. Repeat the part first with the load resistance RL is equal to 3 kilo ohms. Here if the load resistance is equal to 3, V is equal to RL VI upon R plus RL, since the load resistance is 3 kilo ohms, 3 into 10 raised to 3 into 16 upon plus 1K plus 3K is equal to 12 volts. Here now you have to compare this voltage with the Zener voltage. V is greater than Vz, so that the diode is on, then it is replaced by a Zener voltage is equal to Vz. Diode is on, then that Zener is replaced by the Zener voltage Vz, so that here it is the input voltage, here it is the 1 kilo ohm, that is resistance, and the voltage of the Zener, it is equal to Vz, and the load current flowing through that load resistance is equal to current IR. Now VL is equal to Vz is equal to 10 volts. The drop of voltage across that load resistance is equal to VL. and the voltage of the Zener diode is equal to Vz is equal to 10 volts. VR is equal to Vi minus VL. VR is equal to input is 16 volts and load voltage is equal to 10 volts. Load voltage is equal to 10 volts because here VL is equal to Vz. Load voltage is equal to the Zener voltage. The changes, how that changes it will take place here, and the Zener is off. VL is equal to V. VL is equal to V, but here when the Zener is on, the VL is equal to Vz. It is not equal to V because here V is 12 volts. When the load resistance it is 3 coulombs, it is 12 volts. Since V less than Vz, diode is replaced by the Zener voltage. Zener is replaced by its voltage, and the VL is equal to Vz. It is equal to 10 volts. It is not equal to V. It is equal to Vz, 10 volts. So that VR is equal to Vi minus VL. It is equal to 16 minus 10 is equal to 6 volts. Iz is equal to IR minus IL. IR is equal to VR upon R is equal to Vi minus VL upon R. 6 upon 10 raised to 3, 6 milliamperes. IL is equal to VL upon R is equal to 10 upon 3 into 3.34 milliamperes. Okay. VL is equal to Vz, that is 10 volts, and R it is RL is equal to RL. It is equal to RL is equal to 3 coulombs. From that you will be getting the current flowing through the load resistance. Now Iz is equal to 6 milliampere minus 3.3 is 2.66 milliamperes. That is current flowing through the Zener diode, and power dissipated in the Zener diode is equal to Vz Iz. So that power dissipated is equal to 10 volts into 2.66 is equal to 26.6 millivolts. From that Pz is less than Pz maximum. Here the maximum power to be dissipated in the Zener diode is specified in the by the manufacturers, that is equal to 30 milliwatts. That is equal to the 30 milliwatts. So that here the 26.6 milliwatt is less than the 30 milliwatts. So that this is the whatever the Zener regulator which is designed, it can be used for the regulations. So that as specified by the manufacturers. Okay. This is how a Zener regulator it is works.